Since the early 1970s, humanity's return to the moon has never seemed so close. Yes, scientific interest in our natural satellite has remained strong over the decades, but space agencies have increasingly favored cheaper and safer robotic missions to carry out research tasks. However, the growing competition between the United States and China is changing the game. Both countries now view the moon not just as an object of study, but as a strategic source of resources. One of these resources deserves special attention. It is among the most valuable elements on Earth and promises to lead humankind into a new era of energy. And that element, the almost mythical helium-3, is exactly what we'll be talking about today. Among the 12 people who have walked on the lunar surface, one of the last was quite an extraordinary astronaut. Harrison Schmitt held a doctorate in geology, making him the first and still the only professional scientist to set foot on another celestial body. His participation in the Apollo 17 mission was no accident. Once it became clear that this would be NASA's final voyage under the Apollo program, the agency wanted to extract as much scientific value as possible from it. They even altered the original crew lineup to include Schmitt. So, on December 11, 1972, together with Eugene Cernan, Harrison Schmitt successfully landed in the Taurus-Littrow Valley. On the moon, the scientist did what his colleagues on Earth could only dream of. He directly studied the local rocks, collected the best samples to send home, and walked, jumped, and often fell under the strange lunar gravity. Those falls, by the way, made Mission Control quite nervous, since the chance of puncturing a spacesuit and the resulting fatal consequences was far from zero. In the years that followed, scientists carefully analyzed the lunar samples, including those Schmitt had collected. They discovered that the moon's soil contains a surprisingly high amount of a remarkable form of helium, known as helium-3. Decades later, Schmitt himself became one of the key advocates for mining this isotope on the moon, leading a pioneering startup in this field called Interlune. To this day, Schmitt continues to promote the commercial development of the moon, something he and many others believe could not only bring humanity closer to living beyond Earth, but also to realizing the dream of clean nuclear fusion. So, what makes this helium-3 so special? Actually, on the scale of the solar system, helium-3 is nothing magical. Most of you met the element helium back in school. It's the second element on the periodic table and the second most abundant in the universe. Its simple atom has 2 protons, 2 neutrons, and, accordingly, 2 electrons, and an atomic mass of 4. But when we talk about the helium that fills the universe and our party balloons, we usually mean its most common stable isotope, helium-4. Of course, like any other chemical element, helium can lose or gain neutrons and turn into a slightly different species with somewhat different properties. These variants of the same atom are called isotopes. In total, 8 helium isotopes are known, but only 2 are stable: the familiar helium-4 and, as you may have guessed, helium-3. Helium-3 also has 2 protons in its nucleus, but only 1 neutron, which makes it lighter and gives it an atomic mass of 3 instead of 4. That the isotope is stable means it can exist for a very long time, billions of years, without decaying on its own, so you can find helium-3 anywhere ordinary helium is present. Since most of the helium in the solar system is, unsurprisingly, in the Sun, that's where we should look for the source of its isotopes. In the core of our star, at temperatures above 10 million Kelvin, the so-called proton-proton chain operates, the main route that turns hydrogen into helium. One of the intermediate products of these fusion reactions is the creation of helium-3 nuclei. Usually those nuclei are consumed in subsequent reactions, but some fraction can be carried upward by hot convective flows. So a certain amount of helium-3 can end up in the Sun's outer layers, in its corona. There are also processes related to solar flares that produce helium-3 in the corona, but the details of those processes are still being studied. The main point is that the solar wind, the stream of charged particles that is about 95% free protons, also contains roughly 5% helium, more precisely helium nuclei, the so-called alpha particles. And among those nuclei, less than 0.1% are helium-3 nuclei freely roaming the solar system. So our whole system is literally bathed in it. But what exactly makes this isotope special? Truth be told, commercial uses for helium-3 today are not very widespread. Demand mostly appeared after the tragic events of September 11th, when there arose a need for special free neutron scanners. Such devices can detect nuclear weapons and smuggled radioactive materials. Helium-3 is used as the detection medium, and tens of thousands of detectors using it were installed in ports and border checkpoints. This non-toxic, non-flammable gas also has excellent cooling properties. It boils at only about 3 degrees above absolute zero, so it's used for extreme refrigeration of technical systems. Companies like Google, Amazon, and IBM, for example, cool their quantum computers to temperatures close to absolute zero, which exponentially increases their performance. The cryogenic properties of this isotope are also used in other technologies, including medicine. Considering all this, the current global demand for helium-3 is only about 25 kilograms per year. Nevertheless, demand is rising fast, and the reason isn't just cooling. Increasingly, you'll see helium-3 called one of the key materials of the future. Already in the United States, the question of helium-3 extraction is being equated with national security. And the whole point is that helium-3 is the holy grail of thermonuclear fusion. And fusion is that energy of the future that promises to finally free the world from fossil fuels. Modern nuclear power plants operate on the principle of nuclear fission. The idea is simple. When uranium nuclei split into smaller parts, they release a tremendous amount of energy. This energy can be used to heat water and turn it into steam. The steam then drives a turbine, which, spinning at high speed, generates electricity. The problem with this approach is twofold. First, it's not particularly safe, as history has already shown us. And second, it produces a huge amount of radioactive waste that must be stored safely for what is essentially an indefinite period of time. So naturally, scientists have long been searching for alternative solutions, and the most promising one is nuclear fusion. Unlike fission, fusion works the other way around. 2 or more atomic nuclei combine into one, releasing energy in the process. In fact, this is the very reaction that powers our sun and all the other stars in the universe, and it does so without leaving behind the dangerous radioactive waste we struggle with on Earth. Of course, the idea of creating a miniature sun on Earth sounds thrilling, even a bit romantic. So naturally, scientists tried it, and they're still trying. It turned out that even after managing to recreate the necessary pressure and temperatures of hundreds of millions of degrees, every known material on Earth simply melts under such extreme conditions. So researchers had to invent reactors in which the reaction happens without touching the walls of the device itself. They designed a kind of thermos that keeps the hot substance, plasma, suspended using powerful magnetic fields. These experimental machines of the future are known as tokamaks. They're not the only way to achieve fusion, but they're the ones scientists have pinned their greatest hopes on. So what fuel do these machines use? Well, by looking at the stars, we know which chemical element is the most fusible, meaning it requires the least energy to make 2 of its nuclei merge. Naturally, that element is hydrogen, but some of its isotopes are even more fusible. If you've heard of objects called brown dwarfs, you might know that the pressure and temperature inside these failed stars aren't high enough to ignite regular hydrogen. Yet they still produce some energy because their cores burn a hydrogen isotope called deuterium. Deuterium has 1 neutron in its nucleus, which makes it heavier than ordinary hydrogen, but it fuses at lower temperatures and pressures than the most common isotope. Luckily, there's plenty of deuterium on Earth. It's found in water, and roughly 1 out of every 6,000 hydrogen atoms is a deuterium atom. Considering both its abundance and its relatively low fusion temperature, only about 100 million degrees Celsius, deuterium became the obvious choice. The first obvious advantage of this method was safety. If, for any reason, the reaction stops, the plasma simply cools down and turns back into gas. In other words, the purity of the process makes catastrophic accidents virtually impossible. However, since you don't see a wave of fusion reactors being built outside your window, it's clear that this method still has some major challenges. It quickly became apparent that the energy released during the reaction wasn't enough to compensate for the energy spent to ignite and sustain it. Simply put, physicists were losing more energy creating and confining plasma than they were getting back from the fusion itself. As a result, deuterium-deuterium fusion is no longer considered a commercially viable solution. Instead, scientists turned to another possibility: fusing deuterium with tritium, another isotope of hydrogen, but heavier. It has 2 neutrons. For this reaction, the temperature threshold is about half as high, roughly 50 million degrees Celsius, which means lower energy costs to start and maintain it. But of course, there are significant downsides. First, the main byproduct of this reaction is high-energy neutrons. Since neutrons carry no electric charge, magnetic fields can't contain or control them. So these fast-moving particles simply crash into the surrounding material, literally damaging and degrading it. And there's nothing you can do about that. Because of this, deuterium-tritium fusion reactors need heavy shielding and regular replacement of materials exposed to neutron bombardment. Second, the energy produced in a deuterium-tritium reactor comes in the form of neutral particles, not charged ones, meaning it can't be directly converted into electricity. Instead, it must first be transformed into heat, which is then used to boil water and spin a turbine, the same old steam cycle we use in traditional power plants. All of this, material degradation, shielding, large cooling towers, and steam turbines, drives up the cost of producing electricity, making this approach far from a commercially attractive option. Even so, tokamaks running on deuterium-tritium fuel remain humanity's most promising attempt to harness fusion power. Scientists keep improving the design, but so far, we still haven't reached the long-awaited break-even point, the moment when a fusion reactor produces more energy than it consumes. Physicists even have a running joke about this. When asked, "So, when will we finally master nuclear fusion?" they answer, "About 30 years from now, no more." And, as they like to add with a smile, they've been saying that since the 1950s. There is, however, another interesting and quite promising solution, and that solution is deuterium helium-3 fusion. I should say right away, it's not easy. Such a reaction requires far higher temperatures, orders of magnitude higher than those needed for deuterium-tritium. So igniting and confining it demands much stronger magnets and, in general, more input energy. But what do we get in return? First, the D-He3 reaction releases significantly more energy than the DT reaction. And second, and perhaps most important, it emits a different type of particle: protons. Unlike neutrons, protons are charged particles, which means they can be controlled with magnetic fields. That removes the problem of wall degradation and greatly reduces the danger to human life. Yes, the reaction is not completely neutron-free. A small number of neutrons can still be produced, but the amount is orders of magnitude smaller. You could literally place such a reactor near where energy is needed most, close to big cities, without worrying as much about a potential accident. But the real advantage isn't only the cleaner reaction, it's its efficiency. The kinetic energy of those protons, and I'll stress again, they are charged particles, can theoretically be converted directly into electricity. No more heating water, building turbines, and cooling towers. You simply steer the protons in the right direction and convert their kinetic energy into electric current. So the journey from reactor plasma to your wall socket becomes much shorter, and that possibility looks extremely attractive. Potentially, direct conversion of particle kinetic energy to electricity could yield efficiencies on the order of 70%. An absolute dream for power engineers. By comparison, the thermal efficiency of modern steam power plants can reach up to about 50%, and nuclear fission plants rarely exceed 35%. Moreover, if the fuel were pure helium-3, that is, without deuterium, the reaction would proceed essentially without neutrons at all, making it even safer and more efficient. So is this the source of clean energy we've dreamed about for so long? Maybe, but the key isn't just the technology, as it might seem at first glance. The real key to all of this is helium-3. Where do you find the quantities of this isotope needed to make fusion commercially viable? Yes, the solar wind carries tons of helium-3 across space. But unfortunately, or perhaps fortunately, Earth's magnetic field prevents these charged particles from reaching our planet's surface. The problem is that here on Earth, Helium-3 is extremely scarce, almost non-existent. Most of what we have was trapped during the planet's formation, when Earth captured traces of it from the primordial solar nebula. Deep within Earth's mantle, scientists estimate there could be anywhere from a few 100,000 to 1,000,000 tons of helium-3 locked away. But good luck getting to it. Occasionally, some of it seeps upward and can be detected near volcanoes, subduction zones, where tectonic plates meet, or in areas where natural gas is extracted. Yet these traces are so minuscule that industrial extraction is out of the question. At present, all helium-3 used in industry comes from the beta decay of tritium. Tritium, used in nuclear technology and weapons, slowly transforms into helium-3 over time. So by storing tritium reserves, small quantities of helium-3 can be harvested. This process currently yields about 15 to 20 kilograms per year, which is nowhere near enough for commercial fusion use. In fact, it's already insufficient to meet current demand for cryogenics and other applications, making helium-3 one of the most acute material shortages in the world. According to Forbes, as of 2024, 1 liter of this isotope cost around $2,500. That's roughly $19 million per kilogram. Today, it ranks among the most expensive substances on Earth. So, if the dream of clean energy is still alive, and if helium-3 truly is the key, then, ladies and gentlemen, it's time to look toward the moon. Unlike our planet, the moon has no magnetic field or atmosphere, which means that for billions of years, helium-3 ions from the solar wind have been freely bombarding its surface and gradually accumulating in the regolith, the dusty layer of lunar soil. With every meteorite impact, the precious isotope mixed deeper into the upper few meters of lunar ground. Samples brought back by the Apollo missions showed that helium-3 concentrations in lunar regolith are at least 13 parts per billion and can reach 20 to 30 parts per billion in undisturbed soil. That may sound tiny, but for comparison, Earth's atmosphere contains only 7 parts per trillion of helium-3. And remember the price, millions of dollars for a single kilogram, and rising with demand. If this isotope truly proves vital for industry and can be mined on the moon, it could become one of the driving forces behind a new era of lunar exploration and development. Without a doubt, the technical challenges are enormous. Because helium-3 exists in such low concentrations in lunar soil, any potential mining company would need to process massive amounts of rock and dust. To extract just 1 gram of helium-3, you'd have to sift through roughly 150 tons of regolith. Is that a lot? Well, to power a large city for a single year, we'd need to excavate about 2 square kilometers of the moon's surface, digging down roughly 3 meters deep. Based on the samples collected by the Apollo missions, scientists estimate that the lunar surface contains around 1 million tons of helium-3 in total. If humanity could somehow extract all of it, that could theoretically power our civilization for 10,000 years. After that, we'd either have to find new ways to obtain more, or discover an entirely new kind of fuel. In any case, processing lunar regolith would be technically demanding, and not only because of the sheer volume. The material would need to be heated to about 1,000 degrees Celsius to literally bake out all the trapped gases. These gases would then form a mixed vapor that must be carefully separated into its components. To do that, engineers would cool the mixture step by step, below the boiling point of each element, until they isolate the desired gases. To separate helium-3 from the much more common helium-4, the gas mixture must be cooled to an astonishing 3 to 4 Kelvin, just a few degrees above absolute zero. So, yes, the technology is entirely feasible, but it would require immense amounts of energy. That's why helium-3 separation from ordinary helium remains one of the biggest engineering hurdles. On the other hand, supporters of lunar mining point to valuable byproducts of the process, such as hydrogen, which could serve as fuel. Lunar soil also contains a wealth of metal oxides, from which oxygen can be extracted. And oxygen, of course, is a vital resource in space, not just for breathing, but also for refueling rockets. In general, most of the resources humans need should ideally be produced locally on the moon, since transporting everything from Earth would be, to put it mildly, prohibitively expensive. That's why the ability to build lunar habitats and sustain life directly on site is considered a key step toward humanity's long-term presence in space. This very strategy has been championed for decades by Harrison Schmitt. In his book and public talks, Schmitt emphasizes that Helium-3 could become the trigger that finally brings humanity back to the moon. This time, to stay. In an article for Popular Mechanics, he points out that while government space agencies tend to move slowly, private companies could become the real driving force behind our lunar return, and ultimately, the mining of Helium-3. So, meet Interlune, one of the most promising startups aiming to harvest this precious isotope directly from the moon. The company was founded in 2020 by Rob Meyerson, former executive at Jeff Bezos' Blue Origin, with Harrison Schmitt himself as co-founder and executive chairman. In reality, Interlune's broader mission is to extract a wide range of lunar resources, from industrial metals and rare earth elements to water. But its core goal and ultimate dream remains Helium-3. At least that's what the company's CEO keeps repeating in every interview. And why is Interlune seen as such a serious contender? Well, it's hard not to take them seriously when they show off a full-scale lunar harvester prototype at major exhibitions. In May 2025, Interlune, in collaboration with Vermeer Corporation, a giant in industrial machinery manufacturing, unveiled a prototype of its lunar mining machine. The device, simply called a harvester, is designed to process 100 metric tons of lunar regolith per hour. Like a terrestrial combine harvester, it moves forward, scooping up lunar soil, and then deposits the processed material behind it, leaving the surface looking almost like a freshly plowed field. Despite being about the size of an SUV, the machine is relatively lightweight for mining equipment, weighing only a few tons. While that's an advantage for space transport, it poses challenges on the lunar surface. With the moon's gravity being only 1/6 of Earth's, the machine's low mass makes it difficult to maintain traction when exerting downward force during excavation. But that's far from the only challenge our satellite presents. During the Apollo missions, NASA astronauts and their equipment encountered the moon's notorious fine, razor-sharp dust. It clung to absolutely everything, proved hazardous to astronauts' health, and wreaked havoc on mechanical systems. Even the sample collection tools would jam after prolonged exposure. The temperature extremes on the moon are no less of a challenge, reaching plus 122 degrees Celsius on the sunlit side and dropping to minus 133 degrees Celsius at night. That's an enormous strain on metal components that constantly expand and contract under such conditions. NASA has already learned how to seal equipment to prevent lunar dust from getting into critical mechanisms, but neither rovers nor landers have ever had to perform full-scale mining operations, processing hundreds of tons of this abrasive dust through their systems. At Interlune, engineers say they're well aware of these risks and are designing durable machines, even considering on-site robotic repairs to replace worn-out parts directly on the moon. It all sounds incredibly ambitious, but how much would such an undertaking actually cost? The company isn't rushing to release hard numbers, saying it's still too early for that. However, they speak optimistically, suggesting that establishing the first full-scale mining system, including 5 excavators, processing units, solar arrays, and, of course, transportation to and from the moon, would cost hundreds of millions, not billions, of dollars. So far, Interlune has raised $18 million in investments, along with several grants worth hundreds of thousands. They've also already signed contracts with 2 clients for a pilot extraction mission scheduled for 2029. That's right, in just 4 years, the company plans to send one of its harvesters to the moon. The U.S. Department of Energy has even agreed to purchase the first 3 liters of extracted gas at market price. Meanwhile, companies like Blue Force and Maybell, which manufacture cryogenic systems for quantum computers, are already ready to buy tens of thousands of liters of Helium-3 annually. So Interlune and other startups know exactly what they're working for. Of course, all these timelines depend heavily on transportation logistics, and, as you probably know, that's still a major hurdle. Interlune expects that SpaceX's Starship will begin offering lunar delivery services in the early 2030s, which aligns perfectly with their plan for full-scale mining operations. The company hopes that Starship's 100-ton payload capacity will make shipping relatively affordable, potentially requiring only 1 or 2 flights to deliver all the equipment for a single mining camp. They're also exploring partnerships with smaller landers from companies like Blue Origin and others, though that would mean more launches and, inevitably, higher costs. Another key question is, where exactly on the Moon is helium-3 most abundant? To find out, Interlune has partnered with Astrolab to install a multispectral camera on their Flex rover, designed to detect both the quantity and relative concentration of helium-3 in lunar soil. The rover is scheduled to land near the Moon's south pole later this year, aboard Astrobotic's Griffin lander. A second prospecting mission, called Prospect Moon, is planned for 2027, focusing on sample collection, processing, and direct helium-3 analysis near the lunar equator. The goal is to confirm that the targeted regions are indeed rich in the precious isotope. The schedule is, of course, highly ambitious considering how challenging lunar landings still are, especially for private companies that are only now learning to touch down safely. Meanwhile, China isn't sleeping. The whole world is watching as the country steadily expands its lunar program. Of course, China's ambitions go far beyond pure scientific curiosity. They clearly aim to cement their status as a space superpower, and in doing so, strengthen their geopolitical influence. The Moon, for them, is not just a destination. It's a strategic foothold for both resources and power. The Chang'e missions have already detected minerals containing helium-3, and this precious isotope has become one of the central goals of China's lunar effort. Sure, one could argue that we should protect our natural satellite from industrial exploitation. After all, helium-3 is a finite resource. Its current reserves were formed over 4.5 billion years. Wouldn't it make more sense, then, to focus on renewable energy sources here on Earth instead? The problem is, we live in an imperfect world, one where politics often sets humanity's course. Even if the so-called civilized nations were to oppose lunar mining, nothing would stop China from pursuing it anyway. Control over helium-3, along with the Moon's rare earth elements, could shift the balance of power, not only in space, but back on Earth as well. So, whether we like it or not, the Moon is becoming the next stage of geopolitical rivalry between two very different political systems. Will helium-3 truly become that key resource of the future? We don't know yet, but its potential is immense. Of course, there are skeptics of helium-3, of fusion itself, but there always have been. In my view, whatever the outcome, the coming decades on the Moon will be nothing short of fascinating. And as for when humanity will finally master nuclear fusion, well, the answer is simple: in about 30 years, no more.